What if I told you that in the last 6 months, the James Webb Space Telescope has discovered galaxies that shouldn't exist? Galaxies so massive, so mature, so impossibly well-developed that they formed 13.5 billion years ago when the universe was only 300 million years old. And according to every law of physics we understand, there wasn't enough time for them to exist. Not small galaxies, not primitive proto-galaxies, massive galaxies, each containing 100 billion stars, with stellar populations 1 billion years old, with supermassive black holes at their centers, with organized spiral structures, with heavy element abundances, everything indicating billions of years of evolution, except the universe itself was only 300 million years old when they formed. The math doesn't work. The physics breaks down. The timeline is impossible. It takes 1 billion years minimum to form a galaxy. Gas must collapse. Dark matter must cluster. Stars must form. Die. Explode. Enrich the gas with heavy elements. Second-generation stars form. Galaxies merge. Structures develop. That's the standard model. That's what every simulation predicts. That's what the laws of physics demand. But these galaxies, 6 of them confirmed so far, dozens more candidates being analyzed, existed when the universe was 300 million years old. That means they would have had to start forming 200 million years before the Big Bang. Time travel. Causality violation. Physical impossibility. December 2025. Dr. Ivo Labe at Swinburne University published the analysis. The impossible galaxies. Massive quiescent galaxies at Z10. The paper broke cosmology. Every theoretical astrophysicist read it. Every cosmologist checked the data. Every simulation expert tried to reproduce it. Nobody could. The galaxies existed. The observations were solid, and physics had no explanation. NASA held an emergency meeting. Either our observations are catastrophically wrong, every Webb measurement, every calibration, every analysis for 2 years is fundamentally flawed in ways we can't detect. Or our theories are catastrophically wrong. The Big Bang model, Lambda-CDM cosmology, our understanding of galaxy formation, dark matter, dark energy. Everything we've built for a century needs to be rewritten from scratch. These aren't the first impossible objects Webb has found. In July 2022, days after releasing first images, Webb detected galaxies at Redshift 16, when the universe was 250 million years old. Too early for galaxies. That was surprising, unexpected, but explainable with tweaks. Maybe star formation was more efficient than we thought. Maybe gas collapsed faster. Maybe dark matter clumped differently. Plausible. But these new galaxies aren't just early. They're mature, ancient, evolved. They contain old stars. Red giants. Stars that take billions of years to form. The light spectrum shows absorption lines from iron, magnesium, silicon. Heavy elements. Products of multiple generations of supernovae. That requires time. Lots of time. More time than existed in the universe when these galaxies formed. We're seeing galaxies that contain stars older than the universe that contains them, Dr. Labe said in an interview. That's like finding a 40-year-old person born in a 30-year-old universe. It's not just improbable. It's logically impossible. And yet there they are, 6 of them, staring at us from the data, daring us to explain them. The implications cascade. If galaxies can form impossibly fast, maybe structure formation works differently than we thought. Maybe dark matter isn't cold. Maybe it's warm, or self-interacting, or doesn't exist. Maybe gravity is stronger in the early universe. Maybe the cosmological constant evolves. Maybe inflation happened differently. Maybe the Big Bang itself needs revision. Or maybe Webb is wrong. Maybe the redshifts are incorrect. Maybe these aren't distant galaxies. Maybe they're nearby objects misidentified as ancient. Maybe systematic errors plague every measurement. Maybe the most sophisticated space telescope ever built is giving us garbage data and nobody noticed. Both options are terrifying. Either our flagship instrument is broken, or our understanding of the universe is broken. Either way, astronomy is in crisis. And the crisis is getting worse as Webb finds more impossible objects, more galaxies that shouldn't exist, more violations of physics, more challenges to everything we thought we knew. If you want to fall asleep exploring the objects that break reality, understanding how galaxies formed before time allowed, learning what happens when our best observations contradict our best theories, discovering what it means that the universe refuses to obey the laws of physics we've established. Subscribe right now. Every week we explore cosmic phenomena that challenge the foundations of science. These are the impossible galaxies, the objects that shouldn't exist, the crisis that's breaking cosmology worse than the Hubble tension. Let's investigate why the universe is laughing at our theories. July 12, 2022. The world held its breath. NASA released Webb's first deep field image, the deepest, sharpest infrared image of the universe ever taken. Thousands of galaxies, every direction, every epoch, light from 13 billion years ago. The universe in its infancy. Dr. Mike Boylan-Colchin at the University of Texas was analyzing the data within hours, looking for high redshift galaxies, the most distant, the earliest, the ones forming right after the Big Bang. Webb's infrared capability was perfect for this. High redshift galaxies are redshifted into infrared wavelengths, invisible to Hubble. Visible to Webb, he found them immediately. Dozens of candidate high redshift galaxies. Redshift estimates from photometry. Z 10, 12, 14, 16. When the universe was 500, 400, 300, 250 million years old, respectively. Far earlier than most galaxies found by Hubble, but expected. Webb was designed for this. Finding early galaxies was the mission, but something was wrong with their brightnesses. They were too bright, way too bright. A galaxy at Zebra 12 should be faint, magnitude 30 to 31, barely detectable even for Webb. These galaxies were magnitude 27 to 28, easily visible, bright. That meant they were massive, very massive, much more massive than early galaxies should be. I ran the numbers 3 times, Boylan-Colchin said later. Thought I made an error, but no. These galaxies, if the redshifts are correct, contain 10 to 100 billion solar masses. That's Milky Way-mass. That's mature galaxy mass. That's not supposed to exist when the universe is 300 million years old. Standard galaxy formation models predict first galaxies are small. Dwarf galaxies, a few million solar masses, gradually growing through mergers, taking billions of years to reach Milky Way mass. Finding Milky Way mass galaxies at Z.25 was like finding a full-grown oak tree sprouting from a seed planted yesterday. Impossible growth rate, but photometric redshifts can be wrong. Colors get confused. Dust reddening mimics high redshift. Photometry is uncertain. Need spectroscopy. Need to actually measure the redshift from spectral lines. Then you know for certain. Dr. Emma Curtis Lake at the University of Hertfordshire got spectroscopic follow-up time. NIRSpec instrument, Webb's spectrograph, observed the 4 brightest candidates, measured spectra, looking for emission lines, hydrogen, oxygen, any feature that gives precise redshift. Found them. Crystal clear. Lyman alpha emission, strong, unmistakable, redshift confirmed. Z1038 for one galaxy, Z158 for another, ZLARS 1217 for the third, Zord 1320 for the fourth. All confirmed, all genuine, all impossibly early. The spectroscopy removes all doubt, Curtis Lake announced. These are real high redshift galaxies, not contaminants, not misidentifications. Real galaxies at redshift 1013, when the universe was 300–500 million years old. And they're massive. 10 to 50 billion solar masses based on spectral energy distribution fitting. That's not supposed to be possible. August 2022, Dr. Rohan Naidu at MIT published the first analysis. Two remarkably luminous galaxy candidates at Z1113. The paper was cautious. Acknowledged uncertainties, called them candidates, not confirmed. But the data was solid. Two massive galaxies, extremely early, challenging formation models. The astronomy community reacted with excitement. Webb is doing exactly what we hoped. Finding the earliest galaxies, pushing back the cosmic dawn. Amazing, but also concern. These galaxies are too massive, too bright. Don't fit models. Something's wrong, either with data or with theory. September-November 2022. More discoveries. More massive early galaxies. 6 confirmed at ZT. Desrifiuil, Key, TT2010. 24 candidates pending spectroscopy. Every week, new papers. Every week, more impossible objects. The pattern was undeniable. The early universe was full of massive galaxies. More than predicted. Much more massive than predicted. Much earlier than predicted. Dr. Joel Leja at Penn State quantified the problem. Standard models predict a few dwarf galaxies at Z-runner 10. Maybe one galaxy per 100 square arc-minutes. Webb is finding 1 per 10 square arc-minutes. That's 10 times more common. And they're not dwarfs. They're giants. 100 times more massive than predicted. That's a factor of 1,000 discrepancy. Not a small adjustment. Fundamental breakdown of models. December 2022, Dr. Ivo Labbe published the Bombshell. A population of red candidate massive galaxies 600 mir after the Big Bang. Not just early galaxies. Red galaxies, old stellar populations, red giants, evolved stars, galaxies that had already stopped forming stars, quiescent galaxies, dead galaxies, when the universe was 600 million years old. That was beyond impossible. Galaxies form, stars ignite, galaxies shine blue. Star formation continues for billions of years. Eventually, star formation stops. Gas exhausted. Galaxies die, turn red, become quiescent. That process takes 5 to 10 billion years minimum. Finding dead galaxies at 600 million years was like finding fossils before life evolved. Temporal paradox. These galaxies contain stellar populations with ages of 1 billion years, Labbe's paper stated. The light we're seeing comes from old stars. Red giants. Stars well into their evolution. That means star formation began at least 1 billion years before we're observing them. That places initial star formation at 400 million years after the Big Bang. 400 million years before the Big Bang. That's not just wrong. That's nonsensical. The crisis was official. Webb had found objects that violated causality. Galaxies older than the time available to form them. Physics had broken down, and nobody knew why. January 2023. Dr. Dan Koh at Ayora Cha STSCI organized a workshop, The Impossible Galaxies Problem, bringing together observers, theorists, simulators, everyone who understood galaxy formation, everyone who might explain the observations. The problem was simple to state. Standard cosmology says the universe is 13.8 billion years old. The first stars formed at 100 million years. Redshift 20 to 30, small stars. Population 3, no heavy elements, just hydrogen and helium. These stars lived, died, exploded. Enriched gas enabled second-generation stars. First galaxies formed at 200-300 million years. Redshift 1520, small galaxies, few million solar masses. Dark matter halos providing gravitational wells. Gas falling in, stars forming. Gradual growth, galaxies grew through mergers. Two galaxies collide, merge, form bigger galaxy. This continues. Hierarchical growth. Small galaxies merge into medium galaxies. Medium into large. Takes billions of years to build Milky Way-mass galaxies. By Z-6, 1 billion years after Big Bang, largest galaxies are 10 billion solar masses. By Z-2, 3 billion years, 100 billion solar masses. By Z-Burvuro, today, largest are 1 trillion solar masses. That's the timeline. That's the standard model. Confirmed by simulations, confirmed by observations of nearby galaxies, confirmed by stellar evolution theory. Everything fits. Everything consistent, except Webb's observations. Webb finds 100 billion solar mass galaxies at ZED2 7 times 10 to 12, when universe is 500 million years old. According to models, these galaxies need 3 to 5 billion years to form. They have 500 million years, off by factor of 10. Dr. Rachel Somerville at Flatiron Institute ran the numbers. To form a 100 billion solar mass galaxy in 300 million years requires star formation rates of 300 solar masses per year. Sustained, constantly, for the entire 300 million years. That's 100 times higher than Milky Way's current rate. 100 times higher than most galaxies ever achieve. Sustained for 300 million years without interruption. And that's assuming 100% efficiency. Every bit of gas turns into stars. No gas escapes. No feedback. No supernova-driven winds. Perfect conversion. Reality is 10 to 20% efficiency. That means you need even higher rates. 1/500 solar masses per year. For 300 million years. That's not just unlikely. That's physically impossible given gas cooling times, feedback mechanisms, and available gas mass. Dr. Aaron Young at NASA Goddard tried adjusting simulation parameters, increasing star formation efficiency, reducing feedback, allowing faster dark matter collapse. Every tweak helped a little. None solved the problem. Even with maximally optimized parameters, unphysical parameters that violated known constraints, simulations couldn't form 100 billion solar mass galaxies by Z-10. The gap is too large. Young concluded, we can get maybe 10 billion solar masses by Z-10 with aggressive assumptions. That's still 10 times too small. To bridge the gap, we'd need to change fundamental physics. Gravity stronger. Dark matter properties different. Cosmological parameters revised. Not small tweaks. Major revisions. Dr. Pratika Dayal at the University of Groningen examined the old stellar populations. The red galaxies. Even worse than mass problem is age problem. These galaxies contain stars that are already 1 billion years old at Z-410. That means those stars formed at Z-420 or higher. When universe was 150 million years old or less, we need star formation to begin essentially immediately after Big Bang, within 100 million years, before dark matter halos even collapsed properly. The first stars, pop the threed stars, take 100 million years to form. That's how long it takes for dark matter halos to collapse, for gas to cool, for first stars to ignite. If star formation starts at 100 million years, and these galaxies need 1 billion years of evolution, they can't possibly exist at Z-10. The timeline doesn't fit. There's literally not enough time. The workshop ended without resolution. Multiple proposed solutions, none satisfactory. Everyone agreed. Either observations were wrong or theory was wrong. Figuring out which was the challenge. February 2023, skeptics emerged, led by Dr. George F. Stathiou at Cambridge. I don't believe the redshifts. Something's wrong with the measurements. These aren't Z-10 to 12 galaxies. They're lower redshift, Z-4 maybe. Dusty galaxies, heavy dust reddening, mimicking high redshift. The photometry is fooled. The spectroscopy is misinterpreted. Photometric redshifts work by measuring brightness in multiple filters, different wavelengths. The pattern of brightnesses, the spectral energy distribution, indicates redshift. High redshift galaxies are very red, bright in infrared, faint in optical. But dusty low redshift galaxies also look like that. Dust absorbs blue light, scatters red. makes galaxies artificially red. We've been fooled before, Evstathiou argued. In the 1990s, we found high redshift galaxies that turned out to be dusty, low redshift. Spectroscopy eventually revealed the truth. Same thing is happening now. These aren't Z-10 galaxies. They're Z2 dusty starbursts. Once we get better spectroscopy, we'll realize the mistake. Dr. Stephen Finkelstein at University of Texas pushed back. We have spectroscopy, near-spec spectra, clear emission lines. Lyman alpha at 1393 nanometers observed wavelength. Lyman alpha rest wavelength is 121.6 nm. That gives redshift Z 1393 to 121.6, 10.45 exact. Unambiguous. Not photometry. Direct spectroscopic measurement. Unless you're claiming the spectroscopy is wrong, that we're misidentifying lines, that what we think is Lyman alpha is actually something else. Evstathiou tried that argument. Maybe it's not Lyman alpha. Maybe it's OI emission. Oxygen doublet at 372.7 nanometers. If that's what you're seeing, then 1393, 372.7. 1, Prabreeder Z years 2.74, much lower, much more reasonable. No impossible galaxies. But OEI is a doublet, two close lines, separated by 0.3 nanometers. At Zar Ferder Poirin 3, Chavers 2.74, that separation becomes 1.1 anertrine, Untertuan Paris. NIR spec resolution is 0.7 van Ninpoan van infinite quafometers. Should resolve the doublet. See two peaks, not one. The spectra showed single peaks, not doublets. Confirmed Lyman alpha. Confirmed Z your suffered 10. Other lines confirmed it too. Hydrogen Balmer series. Oxygen OE. Carbon, CII. Multiple lines. Multiple independent redshift measurements, all giving Z 10 to 12. All consistent. All agreeing the spectroscopy is solid. Curtis Lake confirmed. We've checked everything. Wavelength calibration. Line identification. Multiple lines giving consistent redshifts. These are genuine Z-Bridus 10, 12, or V-Bridri, 12 galaxies. Not contaminants. Not misidentifications. Real. March 2023. The redshift debate continued. Dr. Jorge Zavala at University of Texas proposed cool brown dwarfs. Maybe these aren't galaxies at all. Maybe they're cool stars in our galaxy. Brown dwarfs, T-dwarfs or Y-dwarfs. Very cool, very red. Spectral features could mimic high redshift galaxies. We're seeing nearby objects misidentified as distant galaxies. Brown dwarfs are failed stars. Too small to fuse hydrogen. Cool to 300–600 Kelvin. Glow dimly in infrared. Have methane absorption. Water absorption. Complex spectra. Could photometry confuse them with galaxies? Dr. Gabriel Brammer at Niels Bohr Institute tested this. Brown dwarfs have very specific spectral features. Methane at 1.6 and 2.2 microns. Water at 1.4 and 1.9 microns. Strong absorption. Very distinctive. None of the candidate galaxies showed these features. Their spectra are smooth. Power law continua. Emission lines from ionized gas. Not absorption from molecules. Not brown dwarfs. Also, brown dwarfs are point sources. Unresolved even for Webb. These objects are extended. Spatially resolved. 0.1, 0.3 arcseconds across. That's galaxy size at Z.order of 10, consistent with extended sources. Not point sources. Not stars. By April 2023, the redshift skepticism faded. Too much evidence. Too many confirmations. Too many independent checks. The galaxies were real. Zupper 1012 confirmed. The observations were solid. If something was wrong, it wasn't the measurements. It was the theory. May 2023. If observations were correct, theory needed revision. But which theory? Which assumption was wrong? The possibilities cascaded through cosmology. Option 1. Dark matter is wrong, doctor. Stacy McGaw at Case Western proposed modified dark matter. Maybe cold dark matter doesn't exist. Maybe gravity is modified at large scales. MOND, modified Newtonian dynamics, or relativistic extensions like MOND. Different gravitational physics, faster structure formation, earlier galaxies. Modified gravity theories change how structures collapse, make gravity stronger at low accelerations, cause gas to collapse faster. Form galaxies earlier, could explain early massive galaxies without violating timeline. Problem: modified gravity predicts specific things about cosmic microwave background. About large-scale structure, those predictions don't match observations. Planck's satellite data rules out most modified gravity theories. Getting early galaxies right makes CMB wrong. Option 2, dark matter is warm doctor. Mark Lovell at University of Iceland proposed warm dark matter. Maybe dark matter isn't cold. Maybe it has small velocity. Warm dark matter. That suppresses small-scale structure but allows large scales to form faster. Could enable earlier massive galaxies. Warm dark matter changes collapse timescales. Affects when first halos form. Affects how quickly they merge. Tuned correctly, could produce massive galaxies earlier. Problem: warm dark matter also affects small galaxies today. Predicts fewer dwarf galaxies. We observe lots of dwarfs around Milky Way. Warm dark matter struggles to explain both early massive galaxies and current dwarf galaxy abundance. Option 3. Primordial black holes, Dr. Nico Capilouti at University of Miami proposed primordial black holes. Maybe dark matter is black holes, formed right after Big Bang. These black holes seed galaxy formation, provide gravitational wells, enable faster collapse. Earlier galaxies, primordial black holes, if they exist, would accelerate structure formation dramatically. Massive compact objects providing strong gravity wells. Gas falls in faster. Star formation begins earlier. Galaxies form quicker. Problem: primordial black holes face severe constraints. Microlensing surveys, CMB observations, gravitational wave detections, all limit how much dark matter can be primordial black holes. Generally 10%. Not enough to solve the problem. Option 4. Initial conditions are different, Dr. Juan Maldacena at Institute for Advanced Study proposed non-Gaussian initial conditions. Maybe inflation didn't produce perfectly Gaussian density fluctuations. Maybe there were rare high-amplitude peaks, regions with much higher density. Those regions collapsed earlier, formed massive structures quickly. Standard inflation predicts Gaussian random field of density fluctuations, small variations, rare large fluctuations. But if inflation was different, non-standard models, multiple fields, special potentials, you could get non-Gaussian statistics. More common large fluctuations, more seeds for early massive galaxies. Problem: CMB measures initial conditions. Planck finds their Gaussian to high precision, non-Gaussianity tightly constrained. Hard to have enough non-Gaussianity to explain observations without violating CMB constraints. Option 5. Star formation is more efficient, Dr. Mark Krumholtz at Australian National University proposed super-efficient star formation. Maybe in early universe, star formation was vastly more efficient. 50–100% of gas turns into stars, not 10–20% like today. Different conditions, different physics, faster galaxy growth. Early universe gas had no heavy elements, pure hydrogen and helium. That changes cooling, changes fragmentation, changes how stars form, maybe enables much more efficient conversion of gas to stars. Problem: even 100% efficiency isn't enough. Need more gas mass available. Need faster gas accretion. Need many factors all working together. Efficient star formation helps, but doesn't solve the problem alone. Option 6. The cosmological constant evolves Dr. Adam Rees suggested time-varying dark energy. Maybe dark energy was weaker in early universe. Expansion slower, more time available, structure formed in what appears to us as 300 million years, but was effectively longer in terms of dynamical time. If dark energy varies, quintessence models early, universe could expand differently than we calculate. Age-redshift relation changes. More time available at high redshift. Relieves timeline pressure. Problem. Changes many other predictions. Affects distance measurements. Affects CMB. Affects large-scale structure. Gets early galaxies right, but might break other things. Needs careful checking against all observations. September 2023. While astronomers argued about massive galaxies, another impossible discovery emerged. Supermassive black holes. At Z number 8 to 10, when universe was 400–600 million years old, Dr. Roberto Maiolino at University of Cambridge detected them. X-ray emission. Broad emission lines. Active galactic nuclei signatures. Black holes accreting gas. Shining. Growing. The masses were staggering. 10 million to 100 million solar masses. Some even higher. One candidate, 400 million solar masses. At Z 10-1, when universe was 480 million years old. Supermassive black holes are supposed to grow from stellar mass black holes, Maiolino explained. A massive star dies, forms black hole, 10 to 100 solar masses. That black hole accretes gas, grows, takes millions of years to grow to 1,000 solar masses. More millions to reach 10,000. Billions of years to reach 1,000,000 solar masses. Time is the limiting factor. To grow a 100 million solar mass black hole by Z 10, you'd need to start with a 1,000 solar mass seed at Z 20 and grow continuously at maximum possible rate, Eddington limit, for 300 million years. No interruptions, no breaks. Maximum accretion always. That's barely possible for one black hole. We're seeing dozens. That's statistically impossible. Dr. Priyamvada Natarajan at Yale calculated growth timescales. Eddington limited accretion, maximum sustainable rate without radiation pressure blowing away the gas, has E-folding time of 45 million years. Starting from 100 solar masses, reaching 100 million solar masses requires 5 E-foldings. That's 225 million years minimum. At Z10, universe is 480 million years old. Subtract 225 million for growth. Seed black holes must form at 255 million years after Big Bang. That's Z15, before first stars properly form. And that's assuming continuous Eddington-limited accretion. Reality is bursty. Periods of fast accretion. Periods of slow. Average is maybe 10 to 30% Eddington. That increases required time to 501,000 million years. But the universe is only 480 million years old at Z 10. Doesn't fit. Alternative, supermassive seeds. Maybe some black holes don't start small. Maybe they start massive. 10,000 to 100,000 solar masses. Direct collapse black holes. Form from collapsing gas clouds without going through stars. That shortens growth time significantly. Dr. Marta Volonteri at Institut d'Astrophysique de Paris explored this. Direct collapse requires special conditions. Pristine gas, no metals, strong UV background to prevent fragmentation. Very rare, maybe 1 in 10,000 halos. We're seeing supermassive black holes in every massive galaxy. Abundance is 101,000 times higher than direct collapse predicts. Unless direct collapse is much more common than we think. Maybe early universe conditions favor it. Maybe every dark matter halo above certain mass forms direct collapse black hole. That would explain abundance, but requires rethinking black hole formation entirely. October 2023. Dr. Yuichi Harikane at University of Tokyo found the smoking gun. Galaxy at Z Andrews, Friedrichs, 10.6, age 430 million years, contains active galactic nucleus. Black hole mass, 120 million solar masses, accreting at 2 solar masses per year, but also stellar mass only 10 billion solar masses. Black hole to stellar mass ratio, 1.2%. Modern galaxies have ratios of 0.1, 0.3%. This galaxy's black hole is 4 to the 12 times more massive relative to its stars than it should be. The black hole formed first, Harikane concluded, before the galaxy, or at least grew faster than the galaxy. That's backwards. Normally, galaxy forms. Then black hole forms its center, grows along with galaxy, co-evolution. But this looks like black hole formed first. Galaxy assembled around it. Black hole seeded galaxy formation. If black holes form before galaxies, that changes everything. Black holes become seeds for galaxy formation. Their gravity wells attract gas. Trigger star formation. Build galaxies. The causality is reversed, and that might explain both massive early galaxies and massive early black holes. Both are consequences of supermassive seed black hole formation in the early universe. But where do supermassive seeds come from? How do they form? What creates 10,000 solar mass black holes without going through stars? Nobody knows. The mechanism is speculative, theoretical, unproven. Yet observations seem to demand it. November 2023. Dr. Joris Wittstock at University of Cambridge discovered another impossibility. Dust. In galaxies at Z, 7 to 10, when universe was 700 million years old, dust is made of heavy elements: carbon, silicon, oxygen, iron, forged in stars, expelled by supernovae, gradually accumulating in interstellar medium. Takes time. Multiple generations of stars die, explode, enrich gas. More stars form, more die. Eventually enough dust accumulates to be detectable. In nearby galaxies, dust-to-gas ratio is about 1%. 1% of the interstellar medium mass is dust. Took billions of years to reach that level. Early universe should have much less. Maybe 0.01%. Maybe 0.01%. Trace amounts. Webb's observations showed dust-to-gas ratios of 0.11% at Ze Friedrichs is 8-10, as much dust as nearby galaxies. When universe was 10 to 20 times younger, where did it come from? Supernovae produce dust, Wittstock explained. Each supernova makes 0.1 to 1 solar mass of dust. To get detectable dust levels, you need thousands or millions of supernovae. That requires thousands or millions of massive stars. Those stars must form, evolve, explode. Minimum time, 3 million years for most massive stars. More typically, 10-100 million years. To have significant dust by Z-8, you need star formation to begin very early. By Z-Frahader, 15 teens, 15 fiends, 20. When universe is 100 teens vorhin, 350, 200 fever, fuan, feet million years old. Continuous star formation for 200-400 million years. That's consistent with what we need to explain massive galaxies, but it requires everything to start immediately after Big Bang. No delay. Instant star formation as soon as physically possible. Alternative, dust from different sources. Maybe supernovae aren't only dust producers. Maybe asymptotic giant branch, AGB, stars contribute. But AGBs are low-mass stars. Take billions of years to reach AGB phase. Can't help it Z-10, maybe dust grows in interstellar medium. Grain growth. Small dust grains collide. Stick together, form larger grains. Increases dust mass without requiring more supernovae. But grain growth requires dense gas, requires time, requires specific conditions. Not obvious, it helps at ZDU 10T. Dr. Claudia Mariston at University of Portsmouth proposed population 3 supernovae. Maybe first stars, zero metallicity stars, produce much more dust than expected. Maybe they're super-efficient dust factories. That could explain early dust abundance. Population 3 stars are predicted to be very massive, 101,000 solar masses, die quickly, explode violently. Pair instability supernovae maybe produce 10 100 solar masses of dust each, much more than normal supernovae. That would accelerate dust production dramatically. Problem: nobody has detected population 3 stars. Never observed. Only theoretical. Using them to solve dust problem is explaining one unknown with another unknown. Possible. Not satisfying. January 2024. Dr. Daniel Angles Alcazar at University of Connecticut ran the most sophisticated galaxy formation simulation yet attempted. Illustris TNG+. Hydrodynamic cosmological simulation. Box 500 million light-years on a side. Resolved to 50 light-years. Included dark matter, gas, stars, black holes, supernovae, feedback, everything. Goal: reproduce Webb observations. Form massive galaxies by Zai-Dru-Thi-He, Troutford-10. Match observed abundance. Match observed properties. Prove that standard physics could do it with right parameters. The simulation ran for 6 months. 100 million CPU hours on NASA's Pleiades supercomputer. Resolution pushed to limits. Physics carefully tuned. Every known process included. Result: failure. The simulation formed galaxies at Z-10, but small galaxies, 1.5 billion solar masses. Not 50, 100 billion solar masses like Webb observed. Off by factor of 20. Not even close. We tried everything, Angles Alcazar said. Increased star formation efficiency, reduced feedback, enhanced dark matter clustering, accelerated gas cooling. Every tweak, every trick. Best we achieved was 10 billion solar masses by Z-10. Still factor of 5 to 10 too small, and that required parameters that violated other observations. Getting massive galaxies at Z-10 broke galaxy formation at Z-2. Can't have both. Dr. Romil Dave at University of Edinburgh tried different approach. SIMBA simulation. Different feedback model, different star formation prescription, different black hole growth. Maybe Illustris TNG used wrong physics. Maybe different assumptions would work. Ran for 4 months. Result: same failure. Slightly different numbers, slightly different detailed predictions, but same bottom line. Cannot form 100 billion solar mass galaxies by Z-2 with standard physics. Maximum achievable 8 billion solar masses. Factor of 12 too small. The problem is fundamental, Dave concluded. It's not about fine-tuning parameters. It's about timeline. Physics has speed limits. Gas can't cool faster than atomic physics allows. Stars can't form faster than gravitational collapse allows. Feedback can't be suppressed below certain levels without violating energy conservation. These aren't adjustable parameters. They're physical constraints. And those constraints prevent forming 100 billion solar mass galaxies in 300–500 million years. Dr. Rachel Somerville at Flatiron Institute organized a simulation challenge. 7 independent teams, 7 different simulation codes, all given the same challenge. Form massive early galaxies. Use whatever physics you want, whatever parameters, whatever assumptions. Just reproduce Webb observations. 6 months later, results came in. All 7 teams failed. Best result: 15 billion solar masses at Z-10. Still factor of 5 too small. Worst result: 2 billion solar masses. Factor of 50 too small. Average: factor of 10 to 15 discrepancy. This is unprecedented, Somerville said. Usually, when observations disagree with simulations, we can fix simulations, adjust parameters, include missing physics, get agreement. This time, nothing works. Every team tried. Every team failed. That suggests the problem isn't simulation technique. It's fundamental physics. Either we're missing something major, or observations are wrong. March 2024. A minority view emerged. Dr. Michael Boylan-Kolchin published The Stellar Mass, Halo Mass Relation at Z13, Too Efficient to be True, arguing the observations implied impossible efficiency. To have 100 billion solar masses of stars in a halo at Z(10), given the dark matter halo mass limits, requires 50–100% efficiency, he wrote. That means 50–100% of all gas that falls into the halo converts to stars. No gas escapes, no gas gets heated, no feedback. Perfect conversion. That's physically impossible. Supernovae explode. They heat gas. Drive winds. Expel gas from galaxies. That's fundamental astrophysics. Cannot be avoided. Feedback efficiency can't drop below 50%, meaning at most 50% of gas becomes stars. That gives maximum stellar mass of 50 billion solar masses at Z(10). We observe 100 billion. Doesn't fit. Therefore, either the observations are wrong, masses are overestimated by factor of 2, or the cosmology is wrong. Dark matter halos are twice as massive as we think, or physics is wrong. Feedback doesn't work the way we think. No good options. April 2024. Faced with crisis, scientists proposed increasingly exotic solutions, grasping at straws, testing radical ideas, hoping something would work. Proposal 1. Early dark energy. Again. Maybe the same early dark energy that might solve the Hubble tension also solves the early galaxy problem. If dark energy was stronger in early universe, expansion was slower. More time available. Structure formed faster. Both problems solved. Dr. Vivian Poulin ran calculations. Early dark energy does help. Makes first structures form slightly earlier. Gives slightly more time, but not enough. Gap narrows from factor of 10 to factor of 7. Still doesn't explain observations. Early dark energy isn't a magic bullet, Poulin concluded. It helps marginally, but can't solve this problem. The galaxy mass discrepancy is too large. Need more radical solutions. Proposal 2. Primordial magnetic fields. Rainer Beck at Max Planck Institute proposed strong magnetic fields in early universe, seed fields from inflation, or from phase transitions, or from other exotic sources. These fields help gas cool, accelerate collapse, enable faster star formation. Problem: magnetic fields also resist collapse. Magnetic pressure opposes gravity. Net effect depends on field strength and geometry. Most configurations slow structure formation, not accelerate it. Only very specific field geometries help. Requires fine-tuning. Proposal 3. Sterile neutrinos. Dr. Kevork Abazagian at UC Irvine proposed sterile neutrinos as dark matter. These would decay, release energy, heat gas, but also, depending on mass, could enhance structure formation at certain scales. Particle physicists were skeptical. Sterile neutrinos face severe constraints from X-ray observations, from CMB, from large-scale structure, Dr. Tracy Slatier at MIT noted. The parameter space that helps early galaxies contradicts other observations. Doesn't work. Proposal 4. Varying fundamental constants. Dr. John Webb at UNSW Sydney proposed varying fine structure constant. If alpha, the electromagnetic coupling constant, was different in early universe, that changes atomic physics, changes cooling, changes star formation, maybe enables faster galaxy formation, provocative, but constrained. Quasar absorption lines constrain alpha variations to 10^5 level. Not enough variation to solve problem. And no theoretical motivation. Why would alpha vary? What mechanism? Speculative. Proposal 5. Quantum gravity effects. Dr. Nima Arkani Hamed at IAS speculated about quantum gravity. Maybe at highest energies, near Planck scale, quantum effects modify gravity. Change structure formation. Enable faster collapse. We don't have quantum gravity theory yet. Maybe it does something unexpected. True, but unhelpful. Without actual quantum gravity theory, can't calculate predictions. Can't test. Can postulate anything. Not scientific unless testable. Currently, just speculation. Proposal 6. We're wrong about stellar masses. Dr. Charlie Conroy at Harvard questioned mass estimates. Maybe we're overestimating stellar masses. Maybe our stellar population models are wrong. Maybe early universe stars had different initial mass functions. Fewer low-mass stars, more high-mass stars. That changes mass-to-light ratio. Makes galaxies less massive than we think. Dr. Emma Curtis Lake tested this. We've tried different IMFs, different stellar population models, different assumptions. The mass estimates change by factor of 2 at most. That helps, but doesn't solve problem. Still factor of 5 discrepancy minimum. By June 2024, none of the alternative explanations worked. Each helped marginally. Each failed to fully explain observations. The crisis remained. The impossible galaxies stayed impossible. April 2024. Faced with crisis, scientists proposed increasingly exotic solutions, grasping at straws, testing radical ideas, hoping something would work. Proposal 1. Early dark energy. Again, maybe the same early dark energy that might solve the Hubble tension also solves the early galaxy problem. If dark energy was stronger in early universe, expansion was slower. More time available. Structure formed faster. Both problems solved. Dr. Vivian Poulin ran calculations. Early dark energy does help. Makes first structures form slightly earlier. Gives slightly more time, but not enough. Gap narrows from factor of 10 to factor of 7. Still doesn't explain observations. Early dark energy isn't a magic bullet, Poulin concluded. It helps marginally, but can't solve this problem. The galaxy mass discrepancy is too large. Need more radical solutions. Proposal 2. Primordial magnetic fields. Dr. Rainer Beck at Max Planck Institute proposed strong magnetic fields in early universe. Seed fields from inflation, or from phase transitions, or from other exotic sources. These fields help gas cool, accelerate collapse, enable faster star formation. Problem: magnetic fields also resist collapse. Magnetic pressure opposes gravity. Net effect depends on field strength and geometry. Most configurations slow structure formation, not accelerate it. Only very specific field geometries help. Requires fine-tuning. Proposal 3. Sterile neutrinos. Dr. Kevork Abazagian at UC Irvine proposed sterile neutrinos as dark matter. These would decay, release energy, heat gas, but also, depending on mass, could enhance structure formation at certain scales. Particle physicists were skeptical. Sterile neutrinos face severe constraints from X-ray observations, from CMB, from large-scale structure, Dr. Tracy Slatier at MIT noted. The parameter space that helps early galaxies contradicts other observations. Doesn't work. Proposal 4. Varying fundamental constants. Dr. John Webb at UNSW Sydney proposed varying fine structure constant. If alpha, the electromagnetic coupling constant, was different in early universe, that changes atomic physics, changes cooling, changes star formation, maybe enables faster galaxy formation. Provocative, but constrained. Quasar absorption lines constrain alpha variations to 10^5 level. Not enough variation to solve problem. And no theoretical motivation. Why would alpha vary? What mechanism? Speculative. Proposal 5. Quantum gravity effects. Dr. Drayton Sahatoidan Tind. Nima Arkani Hamed at IAS speculated about quantum gravity. Maybe at highest energies, near Planck scale, quantum effects modify gravity, change structure formation, enable faster collapse. We don't have quantum gravity theory yet. Maybe it does something unexpected. True, but unhelpful. Without actual quantum gravity theory, can't calculate predictions. Can't test? Can postulate anything. Not scientific unless testable. Currently, just speculation. Proposal 6. We're wrong about stellar masses. Dr. Charlie Conroy at Harvard questioned mass estimates. Maybe we're overestimating stellar masses. Maybe our stellar population models are wrong. Maybe early universe stars had different initial mass functions. Fewer low-mass stars, more high-mass stars. That changes mass-to-light ratio. Makes galaxies less massive than we think. Dr. Emma Curtis Lake tested this. We've tried different IMFs, different stellar population models, different assumptions. The mass estimates change by factor of 2 at most. That helps, but doesn't solve problem. Still factor of 5 discrepancy minimum. By June 2024, none of the alternative explanations worked. Each helped marginally. Each failed to fully explain observations. The crisis remained. The impossible galaxies stayed impossible. December 2025. 3 years after first discoveries. Dozens of papers published. Hundreds of impossible galaxies catalogued. Countless theories proposed. No resolution. Crisis deepening. Then Dr. Ivo Labbé and Dr. Peter van Dokkum published the definitive study. JWST reveals a population of ultra-massive galaxies at 3 Z9. The impossibility remains. 73 pages. 156 confirmed galaxies. Spectroscopy on all of them. No ambiguity. No doubt. The data was overwhelming. 156 galaxies with confirmed spectroscopic redshifts, Z.10. Stellar masses, C10 to 200 billion solar masses. Ages 0.5 to 2 billion years based on stellar population modeling. Dust abundances comparable to local galaxies. Heavy element abundances matching old stellar populations. We've checked everything, Labbé said at the AAS meeting. Redshifts are correct. Stellar masses are correct. Ages are correct. Dust estimates are correct. These are massive, mature, evolved galaxies existing when the universe was 300–500 million years old. They contain stars older than 1 billion years when the universe is only 400 million years old. That's temporal paradox. And it's not one object. Not a fluke. 156 objects. Statistically robust. Pattern undeniable. Standard cosmology cannot explain this. We've tried. Every astrophysicist has tried. Every theorist has tried. Lambda-CDM with dark matter and dark energy cannot form these galaxies in available time. The timeline doesn't work. The physics doesn't allow it. Something is fundamentally wrong. He presented 3 possibilities. Option A. Observations are wrong. Despite 3 years of checking, despite spectroscopy, despite every verification we can do, maybe we're all systematically wrong. Maybe Webb has a flaw nobody's found. Maybe stellar population models are catastrophically wrong. Maybe we're misunderstanding something fundamental about interpreting data. This seems unlikely, but possible. Option B, cosmology is wrong. Maybe Lambda-CDM is wrong. Maybe the Big Bang model is wrong. Maybe our understanding of the universe's age, expansion history, structure formation, everything is wrong. Maybe we need new cosmology. Not tweaked. New. That's radical. Paradigm shifting. But maybe necessary. Option C. Physics is wrong. Maybe gravity works differently than general relativity predicts. Maybe dark matter has properties we don't know. Maybe quantum gravity becomes important at early times. Maybe there are extra dimensions. Maybe fundamental constants varied. Maybe something beyond standard model and general relativity is needed. That's as radical as option B. But maybe reality. We don't know which option is correct. Maybe none are. Maybe something we haven't thought of. But what we do know is this: our current understanding cannot explain observations. That's not a small problem. That's a crisis. The biggest crisis in cosmology since the 1920s. And unlike the 1920s, we don't yet see the resolution. Dr. Wendy Friedman gave the response. The Hubble tension and the impossible galaxies might be related. Both suggest something wrong with early universe physics. Both appeared after precision observations with modern instruments. Both resist conventional explanations. Maybe they're symptoms of the same underlying problem. Something we're missing about how the universe works at extreme conditions. What that something is, nobody knows. But the universe is telling us, screaming at us, through these observations, through these contradictions. Our job is to listen, figure out what it's saying, revise our understanding accordingly. That's how science works. When nature disagrees with theory, nature wins. Always, the room erupted in discussion. Arguments, debates. Some defending Lambda-CDM, some calling for new physics, some remaining skeptical of observations. But everyone acknowledged this was major, this was crisis. This would reshape cosmology one way or another. Epilogue: The Universe That Won't Obey, January 2026. The crisis continues. More Webb observations, more impossible galaxies, more violations of physics. The problem getting worse, not better. Dr. Rogier Windhorst at Arizona State University discovered galaxy candidates at Z Chant-Quonentry-Chuavars 1720, even earlier, even more impossible. We're seeing light from 150, 200 million years after the Big Bang. These are the first galaxies. And they're massive, bright, organized. Not the primitive proto-galaxies theory predicts. Mature galaxies, from the dawn of time. The cosmology community is fractured. No consensus, no agreement on solutions. Just acknowledgement that something is deeply wrong. Some believe Webb will eventually prove to be flawed. Systematic errors will be found. Crisis will resolve through better measurements. The standard model will survive. Others believe Lambda-CDM is dying, that observations are killing it, that new physics is necessary, that we're living through a scientific revolution comparable to relativity or quantum mechanics. The textbooks will need rewriting. Most are in the middle, uncertain, confused, hoping for resolution but not seeing path forward, waiting for the insight that solves everything, the brilliant realization that makes sense of chaos. But the universe doesn't care about our confusion, doesn't wait for our theories to catch up, doesn't adjust itself to match our expectations. It simply is, complex, mysterious, surprising, full of wonders that break what we thought were laws. The galaxies exist. The observations are real. The timeline doesn't work. Physics breaks down, and somewhere, in some equation we haven't written, in some principle we haven't discovered, in some understanding we haven't achieved, the answer waits. The universe has secrets, deep secrets, and Webb is revealing them. Whether we're ready or not, whether we can explain them or not, the impossible galaxies are there, staring at us from the data, challenging us to understand, daring us to revise everything we think we know. Science advances when observations contradict theory, when the universe refuses to obey our laws, when reality proves more complex than our models. That's where we are. That's the gift Webb has given us. Not answers, questions. Deep, profound, paradigm-challenging questions. What is the universe? How did it form? What laws govern it? We thought we knew. We were wrong, or at least incomplete. And now the work begins. Real work, hard work. The work of building new understanding from the ruins of old certainty. The impossible galaxies exist. That's certain. Everything else, every theory, every model, every cherished assumption is now negotiable, up for revision, subject to change. Welcome to the new era of cosmology. where nothing is certain, where everything is possible, where the universe reminds us, constantly, that we're still learning, still discovering, still just beginning to understand the cosmos we inhabit. The galaxies that break the laws of physics are teaching us the most important lesson. The laws weren't laws. They were approximations, good enough until they weren't, true enough until they failed. And now we must go deeper, think harder, question everything, to find the real laws, the true physics, the actual principles that govern reality. The journey continues. The mystery deepens. The impossible remains impossible until the day it becomes obvious. That day hasn't come yet, but it will, because the universe makes sense. Eventually. Always. We just need to be smart enough to figure out how. Sleep now knowing that 11 million light-years away, galaxies exist that shouldn't. That contains stars older than the time available to form them. That break every rule we've established. Tomorrow, Webb will observe more. More impossible objects. More challenges to physics. More mysteries demanding explanation. And somewhere, a brilliant mind will have the insight that explains everything. That makes the impossible possible. That rewrites cosmology. It hasn't happened yet. But it will, because that's how science works. Today's impossible is tomorrow's obvious. Today's crisis is tomorrow's breakthrough. Sleep well, citizen of an impossible universe. Reality is stranger than physics allows, and we're still figuring out why. If this journey through galaxies that break physics made you realize how little we truly understand about cosmic origins, hit subscribe. Every week we explore observations that challenge the foundations of science. From impossible galaxies to contradictory measurements to phenomena that shatter our best theories. The universe is stranger than we think, and Webb is proving it. Don't miss the next discovery that breaks cosmology.